Now, in the same way, we could calculate a significance test using sample proportions with the same idea. Again, going back to our Z statistic formula from chapter 17, in order to figure out our p-value, we want to know what's our z-score from a particular set of information. And that formula is based on x bar minus mu naught divided by sigma over root n. And kind of remember the idea here was that we want to know, well, how different is our sample mean than the claim? Remember, there's like h sub 0, the null hypothesis is like our claim is that the mean is this. In our data, we got this. The difference, might be off by 20, might be off by 100, and we want to know how good that is. So we normalize by the standard deviation or the standard error, and that gives us our z-score. From the z-score, we could figure out how far away from the center that is, meaning how unlikely is it that this data will occur, which again would give us our p-value. But it's the same exact procedure. Notice that again, we're replacing x bar with p hat and replacing mu naught with p naught, where p naught would just stand for the null hypothesis when we're using a proportion instead. So let's look at an example. This one says that a behavioral study claims that a record high 23% of Americans are abstinent. In the sample of 1,423 random Americans, 306 reported themselves as abstinent. Set up a significance test to determine if the data is statistically significant in showing a different proportion. So here's kind of like, we have a study that claims that this is true. We take some data and we want to see, does the data reject or fail to reject the null hypothesis? So we could set this up in a similar fashion, where again, P naught refers to our sample proportion, which is 306 out of 1423. And that would be approximately, let's go ahead and do that, 306 out of 1423, be approximately 21.5%, 0.215. That's obviously not the same as the claim, but remember the whole deal with the hypothesis test is, do we have statistically significant evidence against this claim? And that's what we need to figure out via the same exact methodology as we worked on in chapter 17 and so on in the other chapters where we did significance testing. And basically P naught, if we were to set up the null hypothesis, basically that's just the claim, which is that 23% of Americans are abstinent. Or you could call that P, which is the hypothetical actual population. But again, setting up a null and alternative hypothesis, we use the same notation, H sub 0 and H sub A. And just like always, the null hypothesis is always equal. The null hypothesis is that the actual population proportion is the same as the claim, the stated P sub 0, which, you could say that's 23%. And the alternative hypothesis is that it is different. And remember, you don't want to say it's lower because we don't know that. Pay attention to the question because it could say, determine if the data shows is statistically significant that it is lower than the stated goal. But here, since it just says different, we would say the alternative hypothesis would be that the actual population proportion is different from the null, just because of how it's worded. And again, from there, that will affect our outcome in our probability for our p-value. And also easy to get mixed up. Remember, p-values is capital P, which stands for a percentage chance. It's a different percent than lowercase p and p hat and so forth. So it's a little annoying when you're writing this on your paper, right? Because it's easy to get those mixed up. But just pay attention and make sure, one's capital and one is not. But anyways, let's calculate the Z statistic, again, using the formula. So our Z statistic will be equal to the difference between the claim and the null hypothesis. Sorry, the null and the sample proportion, And this would all be divided by the standard error. So again, it might be nice to calculate the standard error first. The standard error is equal to the square root. Also notice here, we're using P naught instead of P hat. So we actually we wouldn't even call it the standard error anymore. You might just call it the standard deviation of the population proportion, because the logic of how null hypothesis works is we're assuming this is true. So we're assuming that it is exactly this, meaning we know the exact standard deviation of the data, which is why you want to not use p hat in this case. You wouldn't be that far off if you use p hat, but it is better to use p sub 0. So actually, let me erase standard error because that's not quite right. And we'll just say that, I'll just write it as divided by p naught 1 minus p naught divided by n. And now let's plug in everything. So we have 0.215 minus 0.23. Just like before, it's like the difference between the claim and our data. And we need to divide by the standard deviation, which would be 0.23 times 0.77, which is just 1 minus 0.23, divided by the sample size, which is 1,423. And doing all this math, let's use parentheses to make sure we get everything right. 0.215 minus 0.23 divided by the square root of 0.23 times 0.77 divided by 1,423. Assuming that I got all that in, I think it looks good. We get our Z score or Z statistic of negative 1.345 approximately. And again, we can round that to the nearest, oops, that's not the right button. We can round that to the nearest 2 or 3 or 3 or 4 sig figs. Because how we use this is the next goal is to find the p-value. Again, we don't need table C here because this is a Z score. So we need to go to table A to look up what's the resulting p-value. So let's search up a Z table. Or we could use the one in the book from table A. And we want to find a Z score of negative 1.345. So negative 1.345, that would round to negative 1.35. So let's just use that one. Negative 1.35 would be right there. So approximately 0.0885, let's say. So our p-value. Another way you could do it is if you put a little tail under p, it can kind of imply that it's a capital P instead, which I'd say probably don't need to bother doing that. But, I'll go ahead and just differentiate between lowercase p, which stands for proportion, and capital P, which stands for probability. And in this case, we get 0.08. Sorry, what was it again? It was negative 1.345, so negative 1.345 is about 0.885. We got approximately. And if we want a more accurate answer for our p-value, we could use a calculator. We'll do that in a second. But actually, there's one thing that I have forgot to be careful about, which remember when it's two-tailed or two-sided, as ours is, don't forget you need to double the p-value. Because if we're sketching out what this means, again, we have a perfect normal distribution like this. We have our mean, which is here, p naught, and what we get is negative 1.34 for our Z score, which is a little bit less than, a little bit past 1 standard deviation away. Again, what that's probability represents is, about 8% of a chance, about 8% chance that it will be to the left of this curve. But remember, since it was a two-tailed test, we don't know whether our data will be smaller or larger than the actual mean. So there's an equal chance that there would be that our data would randomly be higher than that Z score of positive 1.34, and we need to also add that into our probability. So remember, you want to double that answer when you're dealing with a two-sided test from the from the Z table, I mean. And so if I, double 0.0885 times 2, that would give me approximately 17.8%. Or again, usually we write it as a decimal, so 0.177 is the p-value we care about. Again, we're using table A or a Z table in order to figure these things out. And also, we could do this with a calculator. Let's just check it out because, as I said, it's a little bit inaccurate because there was a little bit of rounding in here, but our calculator will do a more accurate job. if we go to stats tests and go to one proponent Z test. Again, this is a not proponent, proportion. This is a proportion problem, and we're using a normal distribution, and it's a test. So here our null hypothesis was that the sample proportion was 0.23, and then we had 306 Americans reporting as abstinent out of 1423 in our sample. And we have a two-sided test that's already set, but you can change it as well like usual, and we could hit calculate. And what it gives us is our z-score, which is a little different than what we calculated. Most likely because we rounded this a little bit as well. Again, if you want to be more accurate, just use a fraction, don't round. And, it means our p-value was slightly off, but close enough at the end of the day. And then moving back to, again, our conclusion, that's always what, the last part of a problem is, can we understand what this means? But remember, when the p-value is less than alpha, it means it's statistically significant. Here, the p-value is not good. Remember, small is good, big is bad. Here, it's greater than alpha, which is set to be 0.05, meaning this is not statistically significant. And remember what that means is this does not prove that the mean is what it was stated to be. We just fail to reject the null hypothesis in these cases. When your p-value is smaller than alpha, we say we reject the null and we conclude that it is false. Again, not proof. But when we get bad results like this means that there's 17 to 18% chance that you would get this bad of data, even if it were actually 23%, which is fairly likely, and so that's not strong evidence. So again, we'd say that we fail to reject H0, which implies that we really didn't do anything. This data was not good enough to refute the claim.